Hello, I'm SudenurYaprak and with my colleague EmreKurucu, we will present our study on AI-powered network intrusion detection. Our main idea is simple: to detect the rarest, most dangerous attacks. The key factor is not a bigger neural network, it is the quality of the data and how we sample it. I will explain the problem, our pipeline, and the limitation we faced. Then Emre will show how we solved it. Let's start with the problem. Modern networks face constant automated attacks and we can't check all this traffic by hand. So we need automated intrusion detection. But there is a trap in our benchmark dataset CICIDS 2017. Benign and common traffic is about 99% of all flows. The attacks we care about most, web brute force and bot traffic, are less than 1%. Why is this a problem? Because a model that always predicts benign reaches about 98% accuracy. On paper, it looks great, but as a security tool, it's useless because it detects nothing. So our goal is clear: high recall and high precision on these minority classes without hurting the benign majority. And we don't only want attack or not, we want to know which attack, because the response to denial of service flow is very different from a web brute force attempt. This is our system. It has 5 stages. First, we combine and clean the raw CIC flow meter CSV files. Second, we do multi-class array feature selection explained on the next slide, reducing the data to 46 features. The third stage is the one to remember because many papers make a mistake here. We split into 8% training and 20% testing before any oversampling. So the test set contains only real samples. No synthetic data enters the evaluation. Only on the training set we apply smooth to add examples for the rare classes. Finally, we train a residual network, a ResNet, using focal loss. The skip connections keep training stable, and focal loss focuses on the hard examples instead of the easy majority. It's a small network, about 13,000 parameters. Now, feature selection. One of our main contributions. The common assumption is that the features that best separate attack from normal will work for all attacks. This is wrong, and the heat map shows why. The features that work best for DOS and DDoS, the backward packet length statics, that bright band near the top, are almost useless for detecting bots. Different attacks depend on different features. So instead of ranking features once against a single label, we computed correlations for each of the 8 classes separately and took the onion of the strong features. 46 in total, so nothing important for the rare classes removed. Before the multi-class model, we tested the easy version, just benign versus attack. And this is almost a solved problem, 98% accuracy, attack recall of 99%, and an AUC of 0.9996. Only a few attacks are missed. So the message is this: Separating normal from attack is basically done, but treating every attack as one single group is not enough for real security work. We must go multi-class, and that is where it gets interesting. Is the version 9 our best architectural result on the original dataset? And it has two different sides. The majority classes are almost perfect. The DOS, PortScan, DOS, all with F1 scores of 0.98 or higher. But look at the two highlighted rows, web attack and bot. The web attack precision is stacked at only 0.28 and bot F1 stops at 0.52. The symptom is important. The model has high recall, so it finds the real attacks, but it also marks a large amount of benign traffic as web attacks. It produces too many false alarms, and an analyst will soon stop trusting it. So we tried to fix this with algorithms. This slide are honest record of that. Two things worked. The multi-class feature selection improved the web attack recall, and focal loss improved the precision of the mid-level classes like SSH and FTP brute force. But number 3 is a result we include because it failed. We tried smooth ENN, an aggressive cleaning method. It removed almost all borderline web attack samples, and web attack recall dropped to 4%. The lesson for a very rare class, aggressive cleaning can almost delete this class. So the conclusion is the question that guided the rest of the project. If the algorithm is not broken, then what are we feeding it? This slide shows the contradiction that help us answer that question. On the left, every single class reached on AUC above 0.997 in terms of ranking, almost perfect. But on the right, at the same time, web attack precision is only 0.28. How can both be true? If the model ranks almost perfectly but still makes mistakes at the threshold, then this is not a model capacity problem. The network is doing exactly what we train it to do. The real problem must be feature space overlap. The data itself has a problem. So we decided to look inside the data. Emre, over to you.
Thank you, Sude. So we stopped tuning the model and started examining the data. We found 4 clear root causes. First, label noise. The original CIC-IDS 2017 release has known labeling errors and feature generation problems. So the second, and this is the most important one, attempted flows. The dataset contains payload-free traffic that is labeled as an attack. But at the flow statistics level, it looks the same as a normal benign flow. So we were asking the model to separate things that really look identical. And third, validation leakage. The default Keras split takes the last 10% of data as the validation set, but Smooth adds all its synthetic samples at the end. So our validation set was almost completely synthetic, and this quite decorrupted the early stopping signal. And fourth, and the last, is double balancing. The combination of very high small targets and focal loss over-amplified some minority groups and created more false positives. And please notice, none of these 4 problems is the network is too small problem. They are all data and methodology problems, so we fix the map and not the engine. Okay, on to the next slide. So here is the most important rule of our experiment. And I want to be very clear about it. We did not change the architecture. The 14,000 parameter ResNet stayed exactly the same. This was on purpose because it makes the next result a clean, controlled experiment. What we did change was only the data. We moved to the corrected CIC-IDS 2017 dataset published by Englen and his colleagues. So we removed all the payload-free attempted flows. We removed duplicate flows strictly before the train test split to stop leakage. And we used a proper stratified shuffle 10% validation split, so no synthetic data enters early stopping. Same model, cleaner data, and let's see the results. So this is the most important result of the whole project. The bot F1 score on the left chart rose from 0.52 to 0.98, and that is 145 true positives against only 3 false positives. And the overall macro F1 rose from 0.86 to 0.96, and we reduced the remaining false alarms by half when we relaxed those extreme smooth ratios. But the most important point is the proof statement at the bottom. So this bot improvement happened with a completely unchanged architecture. The only thing we changed was the data quality. So this is direct controlled evidence that the original limitation was never model capacity. It was label noise. Fixing data did what no architectural tuning could do. The bar chart on the right shows the full picture. Almost every class is at or near 1.0, and web attack is the only class that is still behind. This brings me to the last technical question. And it is that so. But first, one practical point that matters for real deployment. The default decision threshold in most software is 0.5. For very rare classes, this default value is the wrong choice. So look at the two trade-off curves. For web attack on the left, the best F1 is reached not at 0.5, but by raising the threshold to 0.69. For bots on the right, it is the opposite. The best F1 is reached by lowering the threshold to 0.34. So the deployment message in the orange box is this. A real intrusion detection system needs per class threshold tuning based on operational costs. What is worse for you, a missed attack or a false alarm? So it should not simply use a default software value. Okay, now, why does web attack not reach near perfect scores like the other classes? So this is an honest limitation, and the histogram explains it. If the remaining false positives were just the model being unsure, they would appear at low confidence, but they do not. Look at the chart. The false positives appear at high confidence next to the true positives. The model is confidently wrong because the flows really look identical. And here is the conclusion. Flow level features, packet lengths, interval arrival times, etc., simply cannot represent payload level signatures, such as the actual text of an SQL injection string. Some Bing and web attack flows are permanently impossible to separate in this feature space. So this is not a model limit. It is the theoretical limit of flow statistics. To go further, we would need to inspect the payload, not only the flow. So let me summarize everything in 3 principles here. So one is data quality is more important than model capacity. So label noise and attempted flows created a hard performance limit that no deeper network could pass. So fix the map, not only the engine. 2. Be careful with overcleaning. Algorithmic balancing can help, but it can also hurt. Aggressive smooth ENN almost destroyed our rarest class. So the best solution was a relaxed mode together with focal loss. Enough for support for the minority classes, but without the added distortion. So 3 is validation discipline. A wrong validation split, for our case that is the default training split, quietly causes data leakage. So it destroys the early stopping signal and damages the training, and it is invisible until you look for it. Okay, so finally, our next steps, we have 3 directions. First is dataset expansion. So this means testing this whole pipeline on the newer 2018 benchmark to confirm that our findings also work on other data. So the second one is generative synthesis, which means replacing the simple interpolation of smooth with tabular diffusion models like TabDDPM, which can model more complex minority distributions. And third, operational, moving from our offline batch system to a real-time streaming pipeline for live deployment. And to close, at the beginning, we thought this was a deep learning architecture problem. but in the end, we proved it was a data problem. For rear attack intrusion detection, good data and disciplined sampling clearly perform better than architectural complexity. And that's all for us. Thanks for listening.